Welcome to JavaDay Lviv. You can guess for which company I work for. Exactly. So the most important question, I wish everyone would be in the room already, but the most important question of the day is, who in this room has a Twitter account? That's not bad. That's really not bad for Ukraine. You guys love your Facebook, I know you do. So if you are going to tweet about my talk or any other talk, I encourage you to tweet about all the talks you're attending, and if you liked it or not. I don't know if you want to tweet that out, but whatever. Get the hashtag JavaDay Lviv trending. I'm trying it for the whole day already, but I'm not very successful. So you have to help me out. Get it trending. Twitter has its own VM team, right? So we have our own hashtag. It's called Twitter VM team. If you tweet about my talk, just add that hashtag so that people know that I was actually here. And so let me tell you a little bit about me if you don't know me. I work in JVMs for a very, very long time. And all these 14 years, I worked on compilers. So it's a very interesting topic, but compilers is something that most people don't know about. But it's interesting because it greatly affects the performance of whatever you're running, right? So I used to work at Sun Microsystems and Oracle, later always in the Hotspot compiler team. So I was working mostly on C1 and C2, but actually more C2 than C1. Do people know, let's do a quick show of hands. People know what Hotspot is. Yes, you do, yes. Do you know what C1 and C2 are? Yeah, not really. Do you know what a JIT compiler is? Yes, okay. So quickly, JIT compiler is the compiler in the JVM that translates Java bytecode into native code so that your application runs fast. C1 and C2 are two compilers in Hotspot that are written in C++, and they are two JIT compilers. C1 is like a high throughput compiler. It compiles code quickly so that you don't run interpreted. And then C2 is a high performance, peak performance compiler. So top tier, C2 creates the code where most of your application runs, and so it's fast. So I worked on that. The things I did while I was at Sun Oracle was, the biggest project I've done was JSR 292. That was invoke dynamic. You know, if you ever do, you know, dynamic language stuff, or you use method handles for some things. So we worked on this a long time ago, actually. Holy shit. So there were two different implementations. One was a lot of handwritten assembly code in the JVM. We had some performance issues there, so then we took all that logic and moved it into Java, into the Java Lang invoke package. And so a lot of the logic of invoke dynamic today is implemented in Java in the core library. And I wrote a lot of that code. So if it doesn't work for you and it's broken, you could technically blame me. But I'm always saying that the code I wrote was perfectly fine, and the people who touched after me broke it. That's how I go through my life. So then I did JEP 243. When you've seen Alina's talk right before mine, she kind of explained it already what JVM CI is. It's basically a Java API where you can plug in an external compiler, right? And Graal is the only one right now who implements that interface, but technically there could be more, right? But as of today, we only have one. And then JEP 295 is we introduced ahead of time compilation in JDK 9. Most people don't know about this feature. It's different than what Substrate VM and native images in the Graal VM project, but this one is basically a very simple command line tool that takes in class files, sends it out to Graal, compiles it, and spits out a shared library at the other end. And then Hotspot can pick up that shared library if it's around or not. It can help startup situations, so if you have a problem with startup, it might help, but not always. So we wish it would work better, but it's difficult. And now I work at Twitter. Best company on the planet. Okay, so this is what Twitter looks like. I'm sure you know what it is, right? We have, hundreds of services and thousands and thousands of instances of these services. So, and it's a heterogeneous hardware system on top of it, right? So it's not we own our own hardware, we have our own data centers, but not all the machines are the same, right? So the biggest problem is performance optimization. You could do it by hand, like everyone else does, but it doesn't scale, right? We can't do this for hundreds of services on different machines, and then in a container world where we all live in, you don't even know on which machine it will be scheduled and everything, right? Then you can only handle a few parameters. There are like hundreds and hundreds in the JVM that you can tune. It's very time-consuming, labor-intensive, error-prone, and the biggest problem is that if you've ever done performance tuning at your company, it's like it probably happens at a time when someone is unhappy with the performance, right? And then he sits down for a couple hours, a couple days, and tunes it a little bit, and says, all right. And then that was probably 3 or 4 years ago, if I ask you. That's the case at Twitter, right? There's the tweet service, and I asked the people who are responsible for the tweet service, when was the last time you tuned your service? And they said 3 years ago. So, and then on top, and we do that too. You change your code all the time. And now everyone is doing, multiple deploys a week or even multiple deploys a day. So your optimality that you actually tune for is fleeting, right? It's like it slips away. So the biggest issue is that many services, even at Twitter, operate below optimality, right? You run never on 100% whatever you could. You're probably way down in the 90s or 80s. So performance tuning is important, but it's difficult, and it takes a lot of time. So this is very theoretical. So what is performance tuning, right? You have a function f, and then x are the parameters defined over domain x, and you want to find a configuration A that maximizes f, whatever f is. In a particular case, so f is, I don't know. For example, all the graphs I'm going to show you later, we optimize for less CPU utilization, right? We want to use less CPU because that means we can save. We have to buy less machines to do what we're doing. So that's our F. And then it's always subject to some constraint, G, and constraints could be anything, right? One of the most important constraints is that it still works, right? You can tune the shit out of the JVM, and it doesn't even run anymore. I've done this. You can tune parameters so it doesn't even come up anymore. I mean, one very simple example for this would be if you tune your Java heap size, right? And you say 10 megabytes, it's not coming up, right? So that would be a constraint. Okay, so performance tuning in general, this is how we do it. If you've ever done it, you pick a couple parameters, whatever you want, then you measure it, right? You have to run it yourself. Then you look at what's the outcome, and then there needs to be a person who analyzes the result, right? What we want is to replace that box over there with something that we don't even know about. We don't care, right? As long as we get the best performance out of it. So, okay, optimization of a black box function. So we use something called Bayesian optimization. Does anyone know what Bayesian optimization is? Okay, one person, that's good, and I know you, so it's all right. Because I'm not an expert in Bayesian optimization, I'm really not. I'm giving you a short introduction, and I probably get it wrong. No, I kind of know what it is. Because I want you to better understand all the graphs you're seeing later. Okay, so it's a method to learn, potentially noisy, that's kind of important, objective functions, right? Iteratively and effectively. So it learns from the input you're giving it, and then it gives you a better answer. It finds near optima in a few iterations. That's kind of important, because as I said, if you're deploying multiple times a week, you kind of need a result pretty quickly. You can't wait 3 months until you get a result. You kind of need it now. And then it works well with nonlinear, multimodal, high-dimensional function. That's the most important one, because as I said, you can tune hundreds of JVM parameters if you wanted to, right? That thing can do it. So if you really want to know how it works, my colleague Romke, he explains the whole mathematical background and all that stuff that I know nothing about. He knows how this works. And so you see these slides, like the blue with the graphs with the blue background? I stole all of his slides. And so I'm just giving you a short introduction. Okay, so these, at the x-axis, you see a parameter, 1, with these values, and it affects the performance on the y-axis, so higher is better. And so we did 3 iterations, 3 evaluations with these values, like -2, 0, and 5-ish. And this graph is basically the actual curve that we don't know, right? Because we don't know what the curve is. We would have to, explore the whole space to figure out what the curve is. But that's the actual thing. And we can see where the optima is, right? So what Bayesian optimization does, it takes the evaluations you've done, and then it estimates, it throws in a curve and tells you, okay, here I think that's where it's the best. These are the blue areas. The higher the blue, let me go to this slide, where you can see it overlaid with the actual one. And then we introduce this, the red line, which picks the maximum we have right now. And everything above the red line, the blue areas above the red line, that tells you, that tells the Bayesian optimization can take that to tell you where to look next. Okay, down here, this graph is expected improvement. That's basically the same as the blue area above the red line on top. And the highest points is the ones where we look next, okay? That's what it does right now. So we take this one, obviously, right? And then a little bit to the left, this one, okay? And we've explored that space here, right? So expected improvement is right over there, so we go there next. This one, we see, okay, yeah, it was cool. A little to the right, and we've explored that whole space. And then it tells us, okay, look over here. So we go over here. Well, that was nothing, right? And then we have this one. Oh, actually, the one over there, sorry. And then we have this one over here. Oh, yeah, that's pretty good. And then there are 2 spikes. We do that spike, and the last one, and we found the global optimum. That's what Bayesian optimization does with the input that we are giving it. That's really the whole black box thing that you would have to do as a human if you do it manually. But Bayesian optimization does this for us. So we like it because it's non-parametric, robust, very important because we would like to use this in production. Extensible, yeah, battle-tested on many types of real-world high-impact problems. That's good because then we know it works. All right, so that was the introductory part. That was not that interesting, but kind of important so that you understand what we're about to see. So I've done 2 experiments. Yes, let me tell you first what Autotune is, because this is basically what this talks about. So it's basically a service that we have. I called it BOAS, that's Bayesian optimization as a service. Super funny, huh? And this is based on WetLab. So WetLab's a company that Twitter acquired a few years ago. WetLab is an improvement of an open source Bayesian optimization library called Spearmint. So Spearmint you can still find on GitHub, and you can check that out. WetLab, unfortunately, we didn't open source that. So, and then we have this, and then Autotune is something that we wrote. It's basically a driver to run experiments. So we run in Aurora on top of Mesos. That's what we do. And this is basically an implementation of firing off experiments and running evaluations. So it just goes in and says, okay, start this job with these parameters and then give me the results back. And then Autotune takes whatever it gets back, sends it over to WetLab, to the Bayesian optimization part, and that returns which one to try next. The thing we'd seen earlier, okay? Kind of makes sense? Good. What is Graal? Everyone seen the talk earlier? Don't have to talk about it? Good. It's a great compiler. If you want to know more about Graal, especially how to use it and what to look out for, because it's written in Java and not in C++, as C1 and C2 are. You can watch this talk. I show a bunch of demos, show you how much heap memory it allocates, what the bootstrapping issue is, and so on and so on. Okay, let's come to the experiments. So these are the 3 parameters that I chose to tune for Graal, and they're all inlining related, because if we can improve inlining, we will improve performance in general. So inlining is the mother of all optimization, as we always say. There's one called trivial inlining size. It's basically the number 10 is nodes in a compiler graph. If a method has less than equal 10 nodes in a compiler graph, it will always inline it, no matter what. Then the other one, maximum inlining size, is basically the other end of the spectrum. If a method, even if the profiling tells us, oh, inline this one, if it has more than 300 nodes, it doesn't do it. It doesn't inline it. And then there's this one, small compiled low-level graph size. It's very similar to the second one. It's just at a different level. So there are 2 representations in Graal, compiler graph-wise, and there's one that's called low-level, so it's a little later in the compilation process. Okay, so these 3 I'm tuning, and I've done this before in my previous talk. Before I tried it for the first time with AutoTune, let's put it this way, I actually sat down and did this manually, like a monkey. And I was trying to find out if I could, tune the inlining parameters to squeeze out some performance. So this is the talk, the Twitter's Quest for Holy Grail runtime. You can watch that one. And I just, picked out the slides where you can see this one. The purple one is the experiment, and the numbers in the parentheses are the improvements I could get. So these are GC cycles, and I could improve like a 1.5% less GC cycles by just fiddling around manually for a couple hours, and I could reduce 2% CPU utilization on top of already 13 that Graal gives us by just running on Graal and not C2. So yeah, 2%, it's kind of nice, right? But it's not really a lot, especially, I was happy because I was doing it for a couple hours Friday afternoon. I thought, okay, that's cool. It's some money, right? If you instances and multiplying and so on. So that was cool. So this is basically one of the configuration files for AutoTune, and I just tell it, okay, this parameter, it's a type integer, and I gave it actually ranges. And the reason I did do this is because at the time when I ran the experiments, I wanted the experiments to actually finish and work and be, ready so I can use it in my presentation. But technically, you don't have to give it ranges. All of them, you could say 1 to 1,000. Doesn't matter, right? Because the Bayesian optimization part will figure it out by itself anyway. If you give it the right constraints, it will figure it out. I just gave it some sane ranges so I had results quicker. So we go from 10 to 25 for the trivial inlining size. Then maximum inlining size was default 300. We go from 200 to 500. And then with 200 to 650, and default was also 300. So the test setup, as I always do, I have dedicated machines to run all my benchmarks. Because if you run in a production environment, or if you run on a machine where another process is running at the same time, you have a lot of cross-talking going on and other things that will completely screw up your results. Especially, as I said, in the world we live today, in a container world, there might be 3 or 4 other things running on your same machine. So if you ever do something like this, always use dedicated machines. All instances receive the exact same request, very important. Not only the same number of requests, but the exact same request. And that's important for, let's take the tweet service, right? The tweet service reads and writes tweets. A tweet could be 1 character long or 280. So it would be a very, very different memory allocation pattern if we wouldn't be using the same requests. We use this JVMCI version, this Graal version. It's kind of old already, but doesn't matter. We use the default tier setup with C1 and Graal. I'm not going into details here, but that's basically what you get by default automatically. Good, experiment 1, the tweet service. So the tweet service is a Finagle thrift service. So Finagle is one of these frameworks that we open sourced. It's an extensible RPC system for the JVM used to construct high concurrency servers. No idea what it's doing, doesn't matter. The only thing that's important is it's 92% of Scala code. So pretty much everything we do is in Scala. We have a handful of services that are actually written in Java, but most of our services are 100% Scala. And Graal is very good with Scala. So, objective. So this is the one we want to maximize. So as you can see, it looks for, like here, over here at the end, it says user CPU time. So we're looking for user CPU time. We get this from the container. And then since AutoTune maximizes things, but we actually want to reduce CPU, we do a 1 divided by, the reverse of it. That's our objective. That's what AutoTune should tune for. And then I only used one constraint. It would be better to use more, but in this particular case, it was enough. I look for something called throttled CPUs. So basically, when your service is misbehaving, Aurora or Mesos will just throttle your instance, and then you know it's kind of broken. So that was fine. I was running this experiment for 24 hours. And you see these slices of 30 minutes. These are the evaluations. So one evaluation run I did for 30 minutes. It's not very long, but I know for the tweet service that 30 minutes is enough to get to a steady, stable state. And I also wanted to have as many as I could in a short amount of time. So if we actually would do this in, let's say, in a production environment, we would have long evaluations. But for this one, it's perfectly fine. So when we look at the user CPU time here, so we have experiment as the blue one, and we have a control that we're comparing against, that's the orange one. If the blue line is below the orange one, it's better. If it's above, it's worse. You can look at this one, the same graph in a different way. It's kind of a little bit easier to see as a ratio. Yeah, we can see, yeah, okay, we're better over here. We are improving, and then we find one that's not so good. So remember, the curve we were exploring, that's that. And then at the end, I did, how many did I do? 44 evaluations. And this is the result table you get that AutoTune shows you when it's done. And I was sorting for objective, and as you can see, it's 1.0838. So that's the improvement in percent of the CPU. So we reduced CPU by 8%, which is great. I could just do 2 manually, right? With this one found in like a day, 8% of CPU, it's ridiculous. I mean, when was the last time you tuned your compiler and got 8% out of it? Never. That's the answer. There's another 8, there's a 6.4, another 6.4, so we could guess probably between 6 and 8%. That's the improvement we would see in a production environment. And then you see, the values it found. For the other ones, trivial inlining size 21, default was 10. So we can say, okay, that should probably be a little higher. These are also higher than the default ones because they were 300. Oh, I think the range is here, right? We went to 500 here and to 650 here. Then the bottom of the table looks like this. We see 3 that violated the constraint. So we actually tuned too far. And I remember when I did it manually, that was actually the case. I tuned it too far that it didn't even come up anymore. So that happened 3 times. There was 1 in progress when I shut it down. Yeah, that's about it. Then you can look at the charts with all the evaluations that we did. It's a little difficult to visualize because we are tuning 3 parameters. So it would be a 3-dimensional space. So every data point in this graph depends on 2 other variables that are not the same. So it's like, but it's the best I can show you. I would have to run 3 different experiments and just tune one parameter to show you a graph that actually, a chart that actually makes sense. But it's the best I could do. If you squint a little bit, you can see it's slightly going up, right? So we're 10 is the default, and we can see, yeah, the more we go, the better it gets. We could guess that at around 22, 23, it starts to deteriorate and get worse again, because then there are other effects. If you inline too much, you get into problems like instruction cache and stuff like this. So you can go too far. So this was trivial inlining size, and then this one is the maximum inlining size. It's kind of flat-ish, I would say. There are two outliers up there. They might be outliers because they depend on two other parameters, as I said. So, take it with a grain of salt. This one is very obvious, right? So 300 is not enough, especially for this service. And we are at 600 roughly, and I'm going to 650, and you can still see it's going up. So maybe 650 was not enough. Maybe the 1 to 1,000 or 2,000 would have been much better to explore, because this could actually get better. So what I did then was I was doing a verification experiment, let's say. So I picked the result, the top result that AutoTune found, and actually was running the service for 24 hours with these parameters to see if what AutoTune found we're actually seeing in production. So this is just requests per second. So as I said, every instance receives the exact same request. We can see that here. AutoTune is the red one. So we are looking at kind of 2, 3-ish things. It's always interesting to see if we can reduce GC cycles, because GC cycles, if we can reduce it, it means we are allocating less memory. And GC cycles always affect your latency, right? So you want to reduce them. We can reduce GC cycles for the tweet service by about 3.4% by just using Graal with the default values, basically. And then this is AutoTune. And as you can see, it's roughly, again, the same, up to a total of 7%. So we can tune Graal to reduce GC cycles by 7%. This is actually pretty good, for a service like this. It's not, because this is real world, right? I could show you a benchmark where it reduces by 50%, but it's a benchmark. So same data, slightly differently. It's allocated bytes per tweet, and as you can see, it's kind of flattish over the whole day. So, and then it's again the same 3.5, 3.4, 7, okay? This is the most important one to me, user CPU time. So if we can reduce this, that means we can serve the same number of tweets with less machines. And that means we can save a lot of money, we save electricity, we save cooling in the data center, we're saving the world. Exactly. So by just using Graal 12%, you've seen that on the previous slide. And then this is AutoTune, and we get another 6.2. So up to a total of 18% less CPU. That means we could get rid of 18% of our machines just for this one service. And there are thousands of them. It's a lot of money. It really is. In my Twitter's Quest for a Holy Grail runtime talk, I talk about this. I cannot tell you how much money we're saving, because I'm not allowed to, and you're recording it. But it's a lot. It really is a lot. I mean, I'm not your whatever product, company, business you are doing is maybe not as big as Twitter, but it's still like, it's a percentage of whatever you do, the expenses you have for your compute, right? So this one's very interesting. It's the P99 latency for getting tweets. And as you can see, the latency, sure, over the day, it kind of fluctuates a little bit, so it's a little tricky to see. And then this is AutoTune. You can see it's better. It's a little hard to tell how much it is. So what I did was I integrated over all the latency times over 24 hours, just summed it up, basically. And this is the result. So just by using Graal, we can reduce tweet latencies by 20% already. And then we get another 8.1 on top of it, so it's 28% faster. If you scroll through your timeline, you get your tweet 28% faster. That means you can read a lot of more tweets, if you have the time. Okay, so I did the same for another service called Social Graph. Social Graph is a centralized and useful abstraction for managing many-to-many relationships at Twitter. It's basically who you are following and who follows you and all these things. So Social Graph is doing this, and I'm picking this one as well, just to see, because we're tuning this one completely separately. And what can we do with this one? So objective, same thing, right? User CPU time. Constraint, exactly the same thing, throttling the CPU. It's just a different name of whatever the chart is. And this is the result. So, this was a different day, the graph looks slightly different, but 30-minute runs again, and this is the outcome. Still hard to tell how much it is, right? We can already see there are a few in there that are actually much better. Okay, here are the results. So we get a 7.6-ish% improvement. The top two are 7.6, then 7.2, and then 6.8. So probably roughly around the 7% mark that we can see an improvement here. Bottom of the table, one violated the constraint. 3 are still in progress. Don't ask me why. It's probably a bug somewhere. And here are the charts. It's kind of the same picture as with the tweet service. If you squint, you can see it. It goes up a little bit like this, and then we have one around the 21 number mark. That's the best one. This one, yeah, kind of flattish, maybe goes a little bit up. And this one, not as obvious as for the tweet service, but there's still a little bit of an improvement. And the outlier, again, totally on the 650 mark. So that was probably not enough. I should have, expanded the range a little bit. So this is, again, the verification experiment that I did. Requests per second. The social graph service is using is using CMS, right? The tweet service was using parallel GC, and so we're using a par new cycles here. And we could only improve that by 1.6% by using Graal. So it's just the way, whatever it does, the logic of the service, we could not escape analyze as many objects. We couldn't get rid of as many object allocations as with the tweet service. It's just different logic. So, but that's the reason why we look at it. So, but if we tune it, we can get out another 3.5%. That's more than by just switching over to Graal. And it's about the same number as what we got with the tweet service. So up to a total of 5% less, still good, right? We'll certainly improve our latencies. And then user CPU time, we can reduce by only 5.5 compared to like a 12% for the tweet service. And AutoTune got a 7.8 out of it then. So, up to a total of 13.3. That's pretty nice. If we would just use Graal, would be cool, but we would be throwing away more than half of the improvement. So that's the thing that a machine learning tool can do for you, and so you don't have to sit there and figure this out yourself. Questions? Everyone? No, don't worry about it. I'm not done yet. It's a rhetorical question if you have questions. So everyone in the room is probably thinking this, right? Well, of course I did. I couldn't come up here and say, well, Graal is that great, blah, 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 and I've not done it with C2. So I've done the same with C2 to see how much we could tune C2 and improve CPU utilization. I picked these 3 parameters that are kind of similar to the ones that Graal has. There's one called max inline level. Graal doesn't have that. It's basically how deep the compiler inlines. If you compile 9 levels deep, if you inline 9 levels deep, it stops, no matter what. So if you use a lot of frameworks and frameworks calling frameworks, sorry. Max inline size is pretty much the one, max inline size we've seen before. The only difference here is the 35 is bytecode size. So it's 35 bytecodes instead of the whatever it was 10 of nodes in the graph. Different metric. Inline small code, it's also different. Graal doesn't do that. It's 2000 is if there's already native code for the method. If it was already compiled and it's bigger than 2000 bytes native code, it doesn't inline it. Don't ask me why. I could tell you a story about it, but I'm running out of time. Same configuration. I go from 5 to 20 just to see if anything changes. 10 to 50, 5,000 to 500 to 4,000 because I thought, okay, let's just explore the space. But again, no ranges would be better. Requests per second, again, 30-minute runs. That's the result. Certainly ones in there that are worse, especially that one. There are ones that are better. Looks like this. And here are the results. So the top one is 5.1. But that seems a little bit like an outlier because then we have a 3.8, a 3.5, and a 3.3. So I'm not sure if we actually would do the verification experiment that I've done with the other ones, because I didn't do it with C2. I ran out of time. Is we would roughly get, I guess, a 3.5% improvement maybe on CPU. And that is the tweet service, and what with Graal we got a 7 or 8, if I remember correctly. So yeah, C2, you can tune it. You can get something out of it, but we are far away from the 18% combined that Graal gives us, plus the tuning from, let's be generous. Let's say it's 5 with C2. It's still ridiculous, right? I mean, yeah, Autotune does a good job, even with C2. It does exactly what it's supposed to be doing. It improves your performance, but the point I'm trying to make is Graal, the way it's written and the way it does inlining and everything, it's much more suitable to be tuned because it's more powerful, if that makes any sense. The bottom of the table, no constraints violated. Interesting to me, man, it doesn't really mean anything, but the ones where they're actually worse, are really worse, like 87. It's ridiculous. So let's look at the charts. You don't have to squint to see what's going on here, right? Default is 9. That's not enough. And I would say that 9, the max inline level 9 for C2, for every application on this planet is not enough. And the whole fucking world runs on Java. So it should be 17 or 18. That would be a good number. This one's completely flat. Doesn't matter what we do with that one. This one's completely flat. That surprised me. I thought actually that the inline small code one would have more effect, but it doesn't. Yeah. So I didn't do, as I said, I didn't do the verification experiment with C2, but we would see some improvement. It would be nice. So, summary. Everyone excited for the summary? I do the summary for all of my talks the same way. It's this. And the reason I'm doing this, and the reason I'm touring around to all these conferences and tell you about how cool Graal is and what you can do with it, is because I want you to try it. And the reason I want you to try it is there's a chicken and egg problem here, okay? So, as you might know, Graal is in OpenJDK as of JDK 10. It was already in JDK 9, but because I made it that way. But since 10, okay? So in 11, which is technically, the latest and greatest version, and I'm sure you all run on JDK 11 in production. Exactly. Oh, you do? We're really crazy. Twitter runs on JDK 8, of course, like everyone else. So, but it's in the JDK. If we, and we, I mean the community, the OpenJDK Java community, if we want a compiler like Graal, which is obviously better, especially for Scala, if we want that compiler to become the default compiler in OpenJDK in Hotspot, we need to show the community, and especially Oracle, that it's a mature and stable compiler. So, since it's experimental right now, we can only make the compiler better if we run more code with it, right? We need to test it. You know, we found a few bugs when we started running stuff, Twitter stuff on Graal. We fixed all of them, and since more than 2 years, we haven't found another bug. So what we want is your shitty production code. And I always say, if you run something, whatever you have, it might be a pet project, it might be, you probably have some staging environment before you send stuff into production. So maybe you can flip the switch there, give it a try. There are, for 11, it would be very easy, but I understand that not everyone can do this. Oracle Labs is providing JDK 8 packages that have Graal in them, so you could swap that out and try that one. If it crashes for you, that would be great, because that means we found a bug. And the reason why I'm touring around and asking you to try it, because I don't want that we find the bugs. Because that means Twitter doesn't work, and then I'm you know, my life is hell, then we all want Twitter to be up. If it runs better for you, cool, let us know. If it runs slower for you, would be very interesting to know why. Maybe you could extract a small test case, file a bug report on GitHub with the Graal team. They'll probably look into it. So these are all the reasons why I'm doing this. I just want the compiler to become more well-known as the default compiler in the JDK, because you've seen what it can do for us. And this is all like money in the bank. Unfortunately, it's not my bank. But, you know, as a company, if Twitter can save money, we can hire more people and do more crazy things, so I don't know what. Yeah, that's my monologue about use it. And with that, I say thank you.